All right, good morning. Welcome back from spring break. I hope it was healthy and none of your houses burned down or anything like that, judging by what I'm hearing from the peanut gallery. So, is everybody turning in their homework assignment? Okay, I will have my feedback to you for about your essays next class. And from there, you can make the edits, and next week you'll post to SemiWiki. So we are almost done with Section 5. Then we're going to be getting into Section 6, which is testing and robustness. So we're almost about as deep as these designs go in terms of, we started out with basic CMOS designs, and then we were going into the physics of it, and then we get into the capacitance, then we've gone into wires, and we've gone into sizing, and here we've now gone into different families. We've talked about pseudo NMOS, domino logic. Here we did these designs. We had these pseudo NMOS, where the whole idea is we have one PMOS gate that's being held up, and we have to size the NMOS transistors such that, because we're going to have these PMOS transistors always on, so we want to have saturation mode, and the NMOS transistors are in linear. That was an example problem. Yeah, is this example problem. You have to show that it's in saturation, prove it's linear, figure out the values, and we figured out that the, actually this is one that we, kind of the last thing we did in class, we found out the ratio is 2/3 and 4/3. And these are known values, so basically by doing this part, we were able to do this problem by using the values here for, we have our inverter, our NAND gates, and our NOR gates. Where we were able to calculate the logical effort and input capacitance. Here we were able to find the power dissipation of a static 32-word and 48-bit ROM. We were able to use our power equations and our knowledge of our PMOS and that we have a certain PMOS transistors of an on current of 360 microamperes per micrometer, and we have 100 nanometer wire. 50% of the bit lines are high, so 30% of 48 times 36 microwatts. From there, we started talking about this concept of dynamic logic, where we're using clock PMOS signals to pre-charge and evaluate. So this has a lot to do with timing. So circuits that are going to run a little slower, you're going to have this phi signal, and phi is going to be going in here to the PMOS transistor. When phi is 0, that means it's going into the PMOS transistor, like we know here. So then, once it goes on, then we're able to evaluate. And the reason why we call it the evaluate stage is because we're able to evaluate the A signal. And then we thought about this concept of what happens if the pull-down network is on during pre-charge. So we have an instance here where we have some sort of instance where it's on during the pre-charge, and we have an instance where they fight each other, and where we have to have PMOS transistor sized in a certain way. So they added this foot transistor, which is tied to phi, so that way it's the opposite. So then if it's 0, that means the PMOS transistor is on and the NMOS transistor is off. And we use that stack effect that we learned about in Section 4 to take advantage of that design to help improve it. Here we then presented all the logical efforts of footed and unfooted dynamic logic. These are, logical effort and parasitic delays of each. These, the naming notation previously up here was up, down, and average. Up meaning going from 0 to 1, down meaning from 1 to 0, and average is an average of those two. Next, we talked about monotonic signals. Its output is greater than or equal to. That means if it's 0, it can be 0 or 1. If it's 1, it has to be 1. That's a problem with this monotonic the dynamic logic. And we were able to prove that because of the fact that the input signals, trying to raise it from 0 to 1 of the NMOS transistors for the evaluate and pre-charge logic. We had to meet that condition. So in order to be able to eliminate that problem, we introduced this concept of domino logic, where they have the evaluation and pre-charge, where you have some sort of domino AND gate in series with a static inverter, and then the same thing, and they just keep going and they fall like a domino. Then we presented this problem. We had a 6-input OR gate with the following circuits. I included a number of assumptions for you here, so that way to reduce the complexity of the problem. Here, designing the static CMOS, then we designed a pseudo NMOS. We figured out the input capacitance, and I showed you how these sizes translate to the solutions we're getting. Then we did the same thing. We calculated the delay and the input capacitance of pseudo NMOS and the domino logic. So this is a very good comparison type problem that would be good on an exam because it shows knowledge of comparison delay, domino effect, pseudo NMOS, static CMOS, sizing. So if you can do this problem, you're going to be in very good shape. Then we started talking about sequential circuits. We started specifically talking about tokens, what a token is in terms of you have this value that's going through a pipe. Then you have D latches and D flip-flops. We talked about the timing. And then I presented a number of different sequential type elements. First, we talked about CMOS latch and the pros and cons, specifically that you're going to have a threshold voltage drop. This is good because at the end of section 6, we're going to be talking about I'm going to present a circuit and I'm going to present a set of problems. You're going to want to refer back to 5.17 through 5.20 because if you see you have a circuit, you have some sort of threshold voltage drop, well, there you go. And I can bet that this will be part of the circuit, and the result would be that you want to change it to a transmission gate, which eliminates that particular problem, but you still have a lot of this non-restoring, and you have some added area. So there's trade-offs to all of these. Then we added a buffer to try to do the restoring logic and fix the noise sensitivity on the output or input diffusion. So then we're going to go over this concept of tri-state feedback. And a capacitor holds a value of a certain amount of time. So what happens if phi is 1? If phi is 1, that means phi bar is 0. That means both of these transistors are off. And if we don't have this feedback, what's going to happen is the output capacitance is eventually going to dissipate its charge, and you're going to have an instance here where it's going to go to 0, and then the inverter is going to make it go to 1. So a good type of problem is what happens if you just have a pass transistor and an inverter, and on the output it goes from 0 to 1 spontaneously. Why would that be? Because there's no feedback, because of the dissipation. Buffered input. Now we've added an inverter to try to get rid of this diffusion on the input, and now it's also non-inverting. We have also added this buffered output. We want to we add a phi here to that way, and since it's going to invert with this, it'll actually restore the signal only when we need it. That way, when this transistor passes, this inverter is going to be off, and it allows the output. When the transistor is off, we're going to be using the sequential element to be able to loop. But however, it has a significantly larger size than your typical transmission gate. It's slower, but it eliminates a lot of those problems. And typically, you're going to see buffered output. Also, we talked about flip-flops. We talked about these latches. We had the whole idea where a latch is going to be multiple. A flip-flop is going to be multiple latches, and we use these transmission gates to propagate the token through. We talked about the difference between flip-flop-based systems, two-phase transparent latches, and pulse latch systems. And here's the different timing constraints of flip-flops. Just you have a clock goes through, and then you have a flop at the beginning, and then a flip-flop at the end, and it's timed. This is why knowing the delay of a circuit is important. So that way, if you need to ensure that you have proper timing so everything gets on the output at the same time, you get the timing of your combinational logic, and you know the time of your flip-flops, and then you make that work. Then you can use this two-phase transparent latch. You have multiple latches per half cycle, and you have these concepts of non-overlapping times. And then pulse latches where you have a short pulse at each clock cycle to activate the latches. And we talked about the different propagation delay, contamination delay, latch and flip-flop, clock to Q, propagation delays and contamination delays, D to Q, and that's where you not just have when you have your clock input, but you have the toggle or the D input to the flip-flop, and then you have your latch setup and hold time. So you have a certain amount of time where the latch needs to be set up, and there's a certain amount of time that needs to be held in order to actually stay at that value. And then this problem is kind of a good description of the differences between the latches, flip-flops, and combinational circuits. Delay constraints, we had setup time failure. You have to ensure that the setup time with combinational logic delay is too great, resulting in sequential element receiving an incorrect token. So you have to, the timing has to be appropriate so that way you're sure that at each clock cycle, the value that we want to be propagated is corrected. For example, let's say if you recall from 385, you have JK flip-flops. The whole point of JK flip-flop, you're ultimately trying to get rid of this portion of the input signal where it's just fluctuating before you have your input. If you have this value and you timing it incorrectly, you could potentially grab the wrong value and pass it along. And then we kind of went over the clock periods for all of these flip-flops. And then I have this huge example problem, like 5.8, 9, 10, and 11 are all part of one problem from the textbook. I broke it down into sections so as we were learning it. But basically the whole idea is it uses the integer execution unit from the Itanium 2. And we have this particular circuit where we have a flip-flop, we have an adder, we have a bunch of other elements coming in from this early bypass mux, and we have a middle bypass mux, we have a resistor with a certain amount of delay, or the resistive wires, and then it's going to come back. So each of these have a certain propagation delay and a contaminant. I'll get to your question in a second, Adam. So the adder, result mux, the bypass mux, and your different wires have different propagation and contamination delays. And based on these equations we presented for the contamination delay and the propagation delay, based on the signals, we were able to calculate these equations, and then we were able to figure these out. So here we had a specific one for the combinational path, that the clock signal, we have the propagation delay for Q, and then the propagation delay and the setup time. We defined the setup time as 90 picoseconds, and we had 1,000 picoseconds that added up from the combinational path, and then we had additional 62 picoseconds. Oh. Yes, Adam.
The resistor, so the 2 millimeters means that it's a 2 millimeter wire, and that's
Mm-hmm.
what
Yeah, so that's what, if we recall from the previous section, we calculated what wire resistance and propagation delay and capacitance based on its length.
Right.
So that's what it is.
Okay, and it's got the ground attached to the resistance wire.
Right. Because if we recall, we had the wire, and then it has this, material underneath of it, and basically what it's going to separate it from the other wire, and we use that to keep the metal separate, but you have some sort of capacitive element between those. So in that case, they're grounded out, which is the base of the wire is grounded out, so it'll propagate it through.
Was this the processor that Alpha made fun of?
That Alpha made fun of?
AMD's Alpha just destroyed one of the titaniums.
I believe so. I'm not 100% certain.
I'm just wondering how quick time of the Alpha is compared to this titanium 2.
Well, AMD's it's kind of a difference in industry perspective. AMD is really all about processing speed, but Intel is trying to focus more on robustness, at least at this point.
Is that what they
AMD is all about processing speed. So remember, we have all these good design requires code compromise. So performance is your primary design metric. What are some of the issues? Like if you're trying to have higher frequency, what's that going to have a trade-off for? High power consumption, right? You got high power consumption, and certain programs you have to have a lot of parallelism. programs, especially if you're playing video games. Those are highly parallel because you're trying to run them on the computer screen. Well, sometimes you have to wait on other elements, so that slows your efficiencies down. So if you're trying to maintain efficiency of piping, then you're going to have a compromise in frequency. So there's pros and cons to all of those things, but so just be saying like I'm the fastest computer doesn't necessarily mean I'm the best computer.
Well, I-64 is another failure.
Right. Well, yeah. That's a whole other thing entirely.
Yeah.
That's poor design. Okay, so we kind of went into the two-phase latch. We calculated the equation of the two-phase latch. So we have our PDQ1 of the first phase, or the second phase, and then the propagation delay for each one. And then we solved that for your propagation delay, and we found out our sequencing overhead. And then using that, we broke down, we also had the clock for pulse latches. So then our self-bypass cycle time is replaced. So we've replaced the flip-flop with pulse latches. And so now we have figured out that our cycle time that requires 1,092 picoseconds. We look at the previous problem, it was 1,152. So by using pulse latches, we were able to reduce our cycle time needed to complete the operation. And then we have these minimum delay constraints. We talked about race conditions, which you guys should be familiar with by now. Minimum delay for a flip-flop circuit, we calculated the equation again. We recall that flip-flops are made of two latches, so this required a latch, a combination of it, and a second latch. And from there, we were able to calculate the contamination delay of the pulse width. And from there, we had this last problem where we're trying to replace this with a pulse width latch. And we have a set of conditions. Will this condition work? In this particular problem, we figured out it did not work. And we added buffers to the pulse latch, and we had to figure out that 103 minus 45, the buffer had to be 58 picoseconds in order to work. And so next we're going to talk about this concept of time borrowing. So we're going to define time borrowing as saying it permits the logic to automatically, quote, borrow time from the next cycle, thereby reducing the time available for data to arrive for the following cycle, or permitting the logic to use slack from the previous cycle. So in this instance, we have data is launching from one rising edge, and if it arrives early, then time is wasted because it's kind of just waiting there, consuming time. And if it arrives late, then we're possibly passing on the wrong token. So what we're trying to do is if something gets there early, and we have time that's required to do the next calculation element, then you potentially want to have this instance where you want to borrow time from the next cycle in order to make it work. And so we calculate the time borrowed for a two-phase latch as less than or equal to. So once you get to this certain amount of time that you can have, your clock cycle time divided by 2 minus your contamination delay of PQ plus your non-overlapping time. So the time that's not overlapping, meaning that you don't have some switching from your input, from your phi 1 and phi 2 that are controlling your input, and they're controlling your latches on your the two latches at each edge of the clock cycle. So the non-overlapping time is, for those of you who can see here at the bottom, here, right? And here. So they're both zero. So you're trying to figure out this non-overlapping time and your delay, and also half of the cycle time. And then for a pulse latch, the borrowing time is going to be less than or equal to the pulse latch plus the setup time. Because that's all you're able to borrow, because it's just a short amount that's being saved in the sequential element. Because the time that you can borrow is the time that's being stored at the latches or the flip-flops at the edge of the cycle. So the entire 5.32, so we're going to start today's lectures here. We have defined time borrowing, and we have stated the equations for the maximum amount of time it must be less than or equal to for a two-phase latch and for borrowing time for a pulse latch. And here we have our two latches, and we have phi 1, phi 2. We have our cycle time is here. So our cycle time half is here. And we have our setup time and our non-overlapping time here. So we have here, and then this element after we have assigned a value for setup, and then once that phi 2 comes down, that's where our non-overlapping time is. So our non-overlapping time takes away from what we can use here. And so that means that we can't borrow this time. We can't borrow this time. So therefore, T borrow is labeled half to here. This is the amount of time that can be borrowed because we're not updating a latch. We're just burning time. And here, once it goes to 0, we switch to second phi, right? So therefore, we're moving on. So we can't borrow this time. And this setup time is the amount of setup time we need to be able to properly propagate the token. So we can't borrow this time either. So let's say for some reason you have some controller and you need to have some sort of longer combinational logic, right? And you can try to borrow this time by having your fees change earlier and then having the second fees change later, so that way you can take advantage of that if the situation permits. And so let's go back to our ALU self-bypass path again. We have modified it to have a two-phase transparent latch. A mid-cycle phi 2 latch is placed after the adder, as shown below. And I have the, so we can zoom out here. So we have our adder, we've replaced our two-phase latch here. The latches have a setup time of 40 picoseconds and a hold time of 5 picoseconds, a clock to Q propagation delay of 82 picoseconds, and a contamination delay of 52 picoseconds, a D to Q propagation delay of 82 picoseconds. So now what we're going to do is we're going to calculate the minimum cycle time for the path and how much time is borrowed through the mid-cycle latch time. If the cycle time is increased to 2,000 picoseconds, how much time is borrowed? So here's how the problem is stated. So remember we called that the time cycle, we have since we have two-phase latches, we're going to have propagation delay and our D to Q propagation delay for each one. It's going to be less than or equal to our cycle time. And I've also brought down our numbers from the previous problem so we can reference them while doing this. The result mux, so I can zoom out again here. Okay, so we have our result mux, which is 60 picoseconds. So that comes from here. The middle bypass mux, 80 picoseconds. The late bypass mux, as we defined 80 picoseconds in the problem. The late bypass mux, 70 picoseconds, which we've defined here. And 2 millimeter wires, we have 1 and 2, 100 picoseconds each. So it becomes 60 plus 80, 60 plus 80 plus 70 plus 200 equals 410. So that's where we get our second propagation delay. Our TPDQ is equal to 82 picoseconds as defined in the problem. Our D to Q1 is also 82 picoseconds, so this becomes 82 here. This becomes 82 here. Here we have our 590 second pico delay for our adder. So we have our adder. It's going to go through result mux, middle bypass mux, 2 wires, and the late bypass mux. So you have to account for the adder here. So we have our latch. And the reason why we set up the problem this way is because we have our first latch. We have our first latch, which we'll someday draw. First latch. And the adder is here. So this part of the equation is our P to Q 1 for the latch plus 590 seconds for the adder, because here's the adder. And then the second latch counts for the result mux, middle bypass mux, and late bypass mux. So 60 picoseconds, result mux, middle bypass mux, late bypass mux, and 1, 2 wires. So that becomes out to 410. You add those up, and it comes out to 1,164 picoseconds. So does it make sense how I came up with this equation? So we have 2-phase latch, phase 1, adder, phase 2, everything else. So since the first half of the, okay, so I kind of went through that explanation. 1,064 divided by 2, remember cycle time divided by 2 is part of our equation for calculating this out. So 582 picoseconds. We also know that the first half of the cycle involves the latch and adder delays and consumes 672 picoseconds. So the way we figured this out, here's that half of the delay. This is where our adders are working for the first latch. And we know that half is 582 by dividing this by 2. So we know that this number is 672 picoseconds. So you can borrow 672 minus 582 equals 90 picoseconds from the second half of the cycle. So what happens, the second part of the problem is what happens when we increase the cycle time to 2,000 picoseconds. The cycle time picoseconds is going to be greater than or equal to 1,164. So that means our cycle time divided by 2 is going to be 1,000 picoseconds. We take the first half of this, our first fee. This is 672, right? It's less than 1,000, so time borrowing is not going to happen. Does that make sense? So the general idea of path borrowing, of time borrowing, is what happens in in this case we have a 2-phase where we have one portion of the fee, one portion of the element requires more time than the other. How much time needs to be borrowed in order to make that work? Does anybody have any questions on that right now?
Where'd you get the 82 picoseconds from?
It's stated in the problem. I'm going to scroll up here for a second for those of you watching on the video later. We've defined the clock to Q propagation delay and the D to Q propagation delay. So this is our first fee and that's our second fee. All right. Does anybody have any other questions? So I get to be a bit of a braggart here. Actually, I'm bragging about the success you guys have had as a class. When I took CMOS at the University of South Florida, we covered all the same material and nothing more than you guys have covered, plus you guys have covered a little more than we did. And the last thing we covered is clock skew. So everything past clock skew is, you guys are kicking some serious butt. So you guys are a month ahead of the USF course. So I'm very impressed. Also, Adam, I was telling you about this. I was up at Princeton last week. I was giving a talk on my TGO methods, and I ran into I actually ran into their CMOS professor, they gave the question on stick diagrams. 40 students in their class, 8 of them just left blank. Princeton students. So I was like, oh yeah, well, my students did much, much better. And he's looking at my notes like, can I have that? I was like, putting the notes up like this requires a lot of work. He wants to do it, he can do it himself. But anyway, so clock skew. Clock skew, you're kind of familiar with this concept already in flip-flops. If you're designing a clock and you have a counter and you have different flip-flops, you have a clock that's going to go to each one, right? So what happens is you want to make sure that the clock gets to each flip-flop at the appropriate time. If you have to get there at different times, you could potentially have multiple flip-flops changing simultaneously. One of the ways they get around that is using gray encoding. But this concept of clock skew, when you don't have gray encoding at the CMOS level, becomes problematic. So we're going to define clock skew here as a phenomenon in synchronous circuits in which the clock signal arrives at different components at different times. So that's the TGO here. Up to this point, we've assumed 0 clock skew in all of our equations. Clocks really have uncertainty in arrival time. They affect the contamination delay and the propagation delay. So here we have an example of 2 flip-flops. We have a clock, and the same clock is going to the second flip-flop. And what happens when you have the worst case scenario is that the launching flip-flop receives its clock late, and the receiving clock receives its clock early. In this case, the clock skew is subtracted from the time from usable computation. Now, the reason why that's important is if you have these going at different times, the output is dependent on what you've done up to that point, right? So then what's going to happen is at the time you're going to propagate the next signal out, you don't have the correct value, and you're going to end up potentially propagating an incorrect token. So you have to worry in these timing calculations, and we're going to have one more problem here involving our Itanium 2 ALU. But the idea is, how do we account for clock skew in the instance of delay? So we have these clocks here, and we have our TPCQs over delay. Additionally, we have our propagation delay here, and we're calculating our combinational logic. And in order to propagate the signal out, we have a setup time, and then this part here is our clock skew. And the reason why this is clock skew is because that's the amount of time that's required before we finally, there's going to be some sort of change in value here that we're not certain is the correct time. This moment here, once T clock skew ends, is the moment we can guarantee the correct value will be on the output. So that's going to be the value that we add to our cycle time in order to ensure that we have properly designed the circuit. And so 5.34 is how we've calculated this problem. The clock period for a flip-flop with skew accounted for must be at most, the cycle time is equal to our time for propagation CQ, propagation delay, plus our propagation delay plus the setup time, plus T skew. So this is TPCQ for our D to Q propagation delay, plus our propagation delay for the combinational element, plus our setup time for the next flip-flop, plus the skew. Therefore, solving for the propagation delay, this means our maximal allowable delay is less than or equal to the cycle time minus that quantity TPCQ plus T setup plus T skew. And we've defined again TPCQ plus T setup plus T skew is our sequencing overhead. So the sequencing overhead is the difference between the combinational element and our sequential element. So recall that our flip-flop definition was just the same thing, except without time skew involved. So next we're going to find a skew-tolerant device, which inherently should make sense. This means that we've accounted for a clock skew. We define it formally as a transparent latch-based system that ensures the full cycle is available for computation. And so the parasitic delays for transparent latches. So we have our delay TPD1 plus TPD2 is less than or equal to the clock delay minus 2t time of PDQ, propagation delay Q, and that the contamination delay must be greater than or equal to T hold minus TCOQ minus time overlap minus time skew. So that these equations are the same, except we've accounted for time skew in the transparent latch. And finally, the time borrow time for a two-phase latch may be found using the time borrow is less than or equal to our cycle time divided by 2. Let me scroll up for those of you in the back. Minus the quantity T contamination DQ here plus non-overlap plus TCQ. So it's the same thing where we had our half of our cycle time. We had phase 1 and phase 2, but now we have to account for skew. So we were able to borrow this amount, some sort of time here, because we had an amount that's greater than half calculated in the first latch or in the second latch, and then we're able to borrow that extra time. But in this case, we also have to account for skew because the skew's at the end after our setup time. So therefore, that cuts into the amount of time that can be borrowed. Jason, do you have a question? Oh, okay. No need to be sorry. No need to be sorry for having questions. You guys pay enough in tuition. But is this making sense to everybody? Kind of what's going on here? We're gonna have one last. Do we have one last question, or is that no? That's it for section 5.
TPD.
TPD2.
Okay.
Yeah.
So
It's TPD1 plus TPD2. So while you guys are writing, what we're going to be covering in the next section, in section 6, is testing and robustness. How do you make your designs work? What happens when you start doing a design and something goes wrong? How do you save yourself lots of time? We're going to go over an example of it's going to be a full adder with some fault. So this section is going to be, here's some error in it, find the error. And this is an important skill because I briefly alluded to this concept of simulate and tweak. Well, that's something that can take hours, sometimes days. And all of you have had coding assignments, I'm sure, have experienced something like that. And I'm going to teach you the Naval Nuclear Power School troubleshooting approach. And you're going to be doing problems like this to actually solve where the fault is. And you're going to see in the second example how using this approach as opposed to simulate and tweak will actually save you a lot of time. So
when you say test, you're talking about just for faults, not for like delays or.
Oh no, this will be. I will say it'll be a fault thing. So not delays. Delays are how can you calculate the amount of cycle time required to meet the constraints of your circuit. For example, we calculated, or we did that problem where we had a 6-input NAND gate, and we had to calculate the size of the PMOS and the NMOS based on whether or not we're just going to use these conventional design that we used, or you had multiple gates linking together. There's different input and output capacitances based on those designs. And so you would do that to try to make sure that you're running your most efficient design. Now, when I took CMOS, and we had a design project where it had to work at 1 kilohertz. So that's not very fast at all. So the key thing is, I'm going to emphasize, and we were given better grades based on smaller design. So you're able to say, okay, we're going to make the smaller design where I can have trade-offs in delays, because I'll meet 1 kilohertz. In fact, we were able to successfully prove that it ran at 12.6 megahertz. But so you basically have to find your design constraint and run from there. I probably answered more than what you asked. You asked me a yes or no question. I went on like a 2-minute spiel.
I like your explanation.
Okay. All right, so let's go to section 6. So testing robustness and pitfalls. So up to this point, you're familiar with MOSFET operation and CMOS operation. You've been able to estimate and optimize combinational circuits using RC delay models and logical effort. Been able to estimate and optimize interconnect delays and and noise. Designed for higher performance and lower area using alternate circuit families. You're able to design the source and effects of clock skew and demonstrate knowledge of contemporary issues in CMOS VLSI design, which you've done through your essays. So now we're going to start developing this concept of troubleshooting. So testing causes a lot of problems. This is where there are people who do testing for a living. If you're good at this, you can get a job doing this, and you will be valuable. Particularly, Intel, they had an error with their floating point, FDIV, in 1994, that it happened only one every 10 billion calculations. But if you're running at 2 gigahertz, that's kind of often. So I've included a website here that you are more than welcome to look up as undergrads. And this is a very thorough description of what actually happens here. So you're more than welcome to look that up. But basically, the general idea is testing. We know we're going to figure out this idea of how do you efficiently test a device. So let's say we have a IEEE 754 adder using mantisses. Therefore, you could potentially have 2 to the 32 possible input combinations for one of the inputs, 2 to 32 input combinations for the other input combinations, and then 2 to 32 times 2 to 32, 2 to the 64. That takes an extremely long time, right? So there are ways to reduce that, and especially at the CMOS level where you have different nodes. We're going to be talking about concepts of stuck-at faults, where stuck-at is kind of simulating a ground. Let's say stuck-at 0 means it's tied to ground, stuck-at 1 is tied to VDD. And so if you have a 8-input logic gate and it has 12 nodes, well, 12, if you have 8 inputs, that's 2 to the 8. But there may be redundant results. And if you have fan out, there's some instances where you can't find them. So we're going to be going over an algorithm that is reduced for if you have a circuit with no fan outs, and then we're going to go over something called the D algorithm, where you're actually going to learn how to find faults where there's fan out. And so, but the first thing I want to do is I want to go over this 5-step troubleshooting method. One, you have to identify the problem. How many times have you been doing code and you see some sort of error and you have no idea what it is and you just try looking for it? You don't really know what the problem is. You're screaming. Try to narrow down what the problem is. You Google the error, figure out, just recognize that a problem exists and observe its symptoms. Step 2, take preventative action. This is not something you have to worry about terribly much in this course, but as electrical engineers, you're going to worry about a lot when you're in industry. The short-term action is meant to put a circuit in a safe condition while work is performed to correct the problem. So if you're working on the instrumentation and control equipment on a naval nuclear reactor plant, you want to make sure that everything's grounded, that you're grounded. You don't want to shock yourself. You don't want to cause a lot of trouble. Also, you want to shut down to a certain point. So you're still having the reactor run, but you have to be able to take out the specific circuit board replace it with a backup circuit board, then you're going to take that old circuit board and troubleshoot it. You want to find out what the exact problem is. So that way, if you can find out the problem, you can perform another corrective action instead of just screwing up boards. Side note, have you guys ever seen the movie Crimson, is it Crimson Tide? And so the issue is they have some sort of electrical error that they can't communicate. In real life, they just take out the board, put in the new board, end of movie. So, oh hey, they want us to bomb things. So how did you get a dog on the submarine? So, hey, determine the cause of the problem. This is where we're going to be using this concept of half-splitting model. Process of elimination, separating the factors that are not causing the problem from those that might be causing the problem. So this is a huge part of it, separating the factors that are not causing the problem. This is where people spend most of their time. They are unable to figure out what's not causing the problem from those that are causing the problem. So I described this half-splitting method. You split the circuit in half again and again, reading following the readings to where the problem is. So when you split it in half and you determine that everything on this side of the half is okay, so you know that this specific output is okay, then you know this half is output is okay, then it must be only to the other output. Then you split that half and figure out from there where your errors are. And we'll go over a couple examples of this. Step 4, correct the problem. You've identified your problem, fix it. And then step 5, you want to return the circuit to normal proper operation. Okay. So here is a small example. We have a full adder. And we have 2 instances here where we have unknown values on the output. So we have X and X, right? And our C output, right? So we identify, we check, and we see 0, 1, 1, 0, 1, 0, 0, 1. We know that our sum output is correct. We see that we have properly input our inputs. There's nothing wrong with the input sequence. So we identify that the problem is we are having undetermined values on our outputs. And specifically, that our outputs are for input combinations 0, 1, 1, and 1, 0, 1. So you take preventative action, like I described in the Navy. You don't have to write all this out. You don't have to write this spiel, but you do want to take preventative action because that's a good fundamental to have. Now determine the cause of the problem. So the first thing we do is we split it in half, right? We split it in half here. We know that our sum is correct, and we know that our inputs are correct, right? So the first thing we can eliminate is our error is not XOR gates. So from here, we're going to want to split it in half again. So we're going to split it here. And so we have these values here for P and Q. We're going to test. We have AND gates. So this is A, B, C, or I've given you these values. In the example problem that we're going to do next, it's an actual example problem, you will have a giant truth table with all of these values already there for you. But we go through there and we see that P and Q are both fine. That these are the values for P and Q that we're expecting. We're expecting, here we have A XOR B and C in for P, and that's what we get. And for Q, we're expecting A and B, which is what we got. So we know that these 2 AND gates are not our problem. So we've eliminated the XOR gates. We've eliminated the AND gates. So now we have narrowed it down to our OR gate. We know that the OR gate has some sort of alternate, but most of the values are correct, except for these specific 2. Okay? So before I scroll down and show you the solution, what do you think could possibly happen? Where I have instances where I have 1 and 0 for P and Q. We compare these two values here, so now that we've narrowed it down, we notice that the only times we're getting X on our output is when we have P is equal to 1 and Q is equal to 0. Think about the design of a OR gate at the CMOS level. What's going on there? What does it look like?
Two PMOSs in series.
Yeah, so we have two PMOSs in series, right? Two NMOSs in parallel. And then we're going to have an inverter here, right? So the inverter seems to be working because we have both 0 and 1 coming on the output, right? So we have an instance where this is actually going to be 0 and 1 here. So P and Q, P and Q. So the instance is 0, 1, 0, 1. So what's supposed to happen at 0 and 1 here? It's going to output a 1, and how's it outputting a 1? Which path?
The PMOS.
Well, it's supposed to output. There needs to be a path. So if it's outputting a 1, it would go through both of here when P and Q are both 0, right? Remember, this portion is a NOR gate, so it's going to be 1, 1, 0, 0, 0. So it has to be 0, 0 in order to output a 1. So it should output a 0, but it's outputting an indeterminate value. So what's the output path supposed to be through?
NMOS.
Which NMOS?
The Q.
The Q, right? So we have a PMOS off, and we have Q. Its path is supposed to go through here, right? From 0 to the output. But we're getting an indeterminate value. So something's up with this transistor here. And so, turns out, we kind of screwed up the design of our NMOS transistor. We forgot to include the NMOS transistor in the design. Dun, dun, dun. And then you correct it by properly designing the OR gate. You put it back in there. And here I have the little check mark. We see that specific instance where we had our problem is now fixed. We plop that back into our circuit. It will work just fine. And now we have found the problem. And so we return the circuit to normal operation. Some other troubleshooting tips and advice. You want to break down. I did include a little, 99 little bugs in the code and 127 little bugs in the code. You want to try to recreate the problem unless there's a personal safety concern. You want to write all testing step conditions down as you go because you want to see what changes you may or may not have made to the circuit. I can't emphasize this enough. If you make changes to the circuit and you don't document it and it creates a different problem, you know what's going to happen? You're just going to make yourself angrier.
Cry a little bit.
Yeah, you're going to cry a little bit inside. And here's the last thing, and this is where our example problem is going to come into play. Never rule out having more than one problem. When you do this is what's going to happen. You change something and then you realize you have a lot more problems, right? Because oftentimes compilers will just stop when you get a certain error. So you fix your error and suddenly you have a lot more, but you didn't address the other problems. So if more than one problem exists, look for common components. So I want to show you this. We're going to do the same XOR gate, but I've seen multiple people have this exact problem that we're going to do, and we're going to solve it in like 5 to 10 minutes. And I've seen them spend days, literally days on it, 2 or 3 days in the lab, 12-hour days. And I go, and they'll, Matt, come here, help me. Sure, and I'll see it, and I go, you're going to hate me when I tell you this. But then I make them do what I'm going to show you do, because you teach a student to fish, and maybe they'll fish forever. Who knows? So here we go. Example 6.1. We have our full adder, and we have a set of values. So this is the whole problem here. You are given. So we have considered a design for a full adder, and we see that our sum value is wrong, and we see that our C out is wrong. Both of these are faulty. Oh crap, right? So simulating and tweaking is going to cause a serious issue, especially because I've given you a big hint earlier, never rule out having more than one problem. So we identify that both of them are incorrect. So here's the thing. First thing we're going to do is we're going to split our circuit in half, and we're going to see what's going on with value 3. Value 3 is Cn, right? They match. So Cn is the C input is not our problem, right? Circuit 4 here is supposed to be A XOR B, right? Well, if we look at it, it's actually equal to A. So we know that something's wrong here. And then we check 5 and 6. We see that 5 and 6 are A and B. We see that 5 and 6 are correct. So our A input is not the error. Our B input is not the error. Our C input error is not the error. But we do know that the output of that XOR gate is an error. So we do know that we have some sort of fault here. But we also know that if we only have this, if this input is wrong, and we have these other inputs correct, we can rule this out for the time being, and then see how the error propagates later. So then, testing for values 7 and 8, what we want to do here, when we split it, we want to check to see if values 7 and 8 are correct based on the current set of inputs. Not the final inputs that we're expecting for the full circuit, but is value 7 equal to 3 and 4? So we check that. Value 7 does in fact equal 3 and 4. We check, does 8 equal 5 and 6? We go through, we do see that and is equal to 5 and 6. So we know that our AND gates are not in problem. And we see, is C out equal to 7 or 8? We check that, and sure enough, it is. So we have also eliminated the OR gate as the problem. So we now know that this half of the circuit is fine. We've eliminated everything. So now you don't have to simulate or tweak anything. Everything over here is fine. Don't touch it. Do not touch. Do not touch. I can't emphasize this enough. You try that. Oh, this. So we see that the C out is wrong, but nothing's wrong over here. So now we want to split this circuit in half again, right? So we split the circuit in half, and we check value 1. We know that value 1 is equal to A, right? So but we know that our A and B inputs are correct. So something's wrong here, but instead of getting A XOR B, we're just getting A. So what this means is the B input is always being read as 0. And we're going to find this later as a stuck at 0 fault. So here's the thing, though. By using the method, we've split the circuit, and we know that we have a stuck at 0 fault here. This is where people waste tons of time. Right here, this next step is where you're going to save yourself hours. Because here's what will happen. You found the error. You fixed the XOR gate. But it doesn't solve all your problems. Because you're still going to have wrong values on the sum. And then you go, what the heck? You throw up your pen. You storm out of the room, and then you flatten your circuit again. You try to figure out what's going on. You start messing around with other things. Wait, I thought this was the problem. I thought everything over here was fine. Then you try again. You start messing around with stuff. You have to continue testing the circuit for this half. So here, we know that this is equal, that we have 1 XOR Cn, and this should put out that value for sum. You check that first before you make any changes to the circuit. And what we find out is our sum is actually equal to A. So it turns out that we have another stuck at zero fault. So this stuck at zero fault is here at this XOR gate. So the reason why there's multiple stuck at zero faults is because you designed the XOR gate in the cell to have the ground. So what people do is they flatten the circuit out, meaning you put all the metal together, you put all metal one, all the polys, all the pins, everything together, VDD. You find this ground, it doesn't fix your problem. You mess with it, you mess with it, you mess with it. You find this one, it doesn't fix your problem because you've reset the circuit, right? So what you do instead is I tell them just fix the ground in the cell and then recompile the circuit, boom, it works. And so that's it. This table is the example of what will actually come on the output if you just fix that first XOR gate and don't mess with anything else. You'll still get wrong outputs and you'll lose your mind. I've seen people spend days on fixing that exact problem we just went over. So hopefully I've taught you guys how to spare some time.
Explain that like you've done that 1,000 times.
Enough times. And you guys are a lot calmer than the people I've had to explain it to. What? Really? Really? This is in the cell the whole time? Okay, so now, let's say you want to do this for a career. You become good at it. There are 3 types of testing for CMOS design. So formal verification is kind of what you guys have done a lot in code. For coming up with a set of tests that confirm the chip performs its intended function. So you design a MIPS processor. You have a certain amount of, you make sure that the register values are loaded, the instruction memory is loaded, the data memory is loaded, and then you run the tests. It confirms that the R-type works, the I-type works. Next, silicon debug. What happens during foundry? Test that confirms the fabricated chip meets design and performance metrics. So you make sure that it runs as fast as you want it to, that it consumes as much power as you want it to. Does it actually have the right capacitance values that you expected? Do the wires work? We're going to go over a number of bugs. I'm going to show you a number of pictures. Give me a split second. I'm going to scroll to the, we'll go over this. There's a number of different things that could potentially happen during silicon test. And you got to go through there and find all of these. All right, so let me go back here. Last, certainly not least, manufacturing tests. Tests conducted on each manufactured chip before shipping to the customer to verify that the silicon is completely intact. Don't want to ship a computer that has broken silicon and it doesn't work. So you have to test to make sure that it does what you want it to do, that it meets the metrics, and that it's actually physically sound. So I kind of gave this example of a 32-bit adder doing, 2 to 31 times 2 times 2 to the 64 input combinations is not efficient, especially if you've proven certain inputs work. If you can come up with a minimum number of test vectors, that improves your time. We're going to go over these concept of corner cases, slow, fast. We know that in order to meet certain design conditions, from switching from 0 to 1, for example, or we want to have certain performance metrics, or we want to make sure that we are properly. We're going to talk about this concept of shmoo plots. We're going to see how circuits work under certain circumstances. And we also went over this concept of logic bugs versus electrical failures. Logic bugs means you've designed the circuit improperly. Electrical failures means you've designed the circuit properly, but you have done something wrong at the electrical level. Some pin didn't come out properly in foundry. You have a stuck at 0 ground in your XOR gate, so your full adder doesn't properly work. Then you're working about dynamic nodes with all these sizings, and we have to domino logic. You have to make sure that everything's working properly. Ratio failures. And their design rule check. Did the DRC that you use to synthesize your chip actually meet actual physics? Which can be a problem. Manufacturing test, you get a speck of dust on a wafer. That's going to kill the whole chip. It has to, as we now know, a speck of dust is actually huge compared to transistors and wires. So now you're actually causing serious problems. And so manufacturing testers are very expensive, i.e. manufacturing testers are well paid. So in order to be well paid, you should understand the concept of test vectors. Layer to layer shorts. Okay, so I can show you this picture here. So we are now talking about different levels. So let's say we have metal one shelving. So we have this concept where things get shorted to one another. They don't properly maintain the differences. Here, this is a metal 5 film particle. So these are supposed to be separate. They're propagating two separate values through the circuit, but they're shorted. And let me get rid of that so you can see. Right? Here, an open defect is it's supposed to connect, but it doesn't. So here you're supposed to have vias that actually connect. Remember we were talking about vias at the pins that are supposed to connect different metals to propagate the signals. As at the foundry stage, it's also called infant mortality. I know. I'm the messenger. Don't shoot me. Patterning defects. You're supposed to have some sort of metal going through the circuit, and you have something went horribly wrong here, and you just have right. Spot.
Actually looks like somebody sneezed.
Yeah. Here you're supposed to have your pin. The metal one's supposed to cover the pin. It doesn't reach. So if you recall from our XOR, or here we just do an inverter, right? So you have our pin goes through the transistor and the output. It's supposed to reach the pin. In this case, this could be an example. This could be a NAND gate where you have two pins and one of them doesn't reach. So now you have an instance where it's all zeros on your output. So let's say this was VDD, it's not getting there. So this is our different layers of testing. This is 6.3 here. So behavioral level, register transfer level, structural level, and physical level. So in 385, we learned about the behavioral level and RTL level, and now we're getting the underlying technology. Recall when I was talking at the beginning of the lecture, and I also alluded to this in 385, about how Moore's Law designers always designed this because they always assume that this is just going to get smaller. But CMOS designers, good computer engineers, are the ones that are going to have to design and test at these levels. So here you have your formal verification, your test vectors that you're going to be putting into your circuit. For RTL level, you have to worry about timing and noise analysis, especially when you have to make sure that you can get from your hit both of your noise margins for the frequency that you want to hit. You also, now that we know much more detail about timing, you have to have a lot of sequential timing analysis. You have to worry about contamination delays. You have to worry about clock skew. You have to worry about propagation delays. You have to worry about the phasing. Now you have to worry about time borrowing. And that goes all into this timing analysis. So now, structural specification, layouts versus schematic. You're actually familiar with this. You've done problems where for example, on example 1, you had 4 different designs of 6 input NAND gates, right? And so that means now you have to worry about different sizing for the different transistors. How does that affect your propagation delay? How does it affect your input and output capacitance? How does that affect your ability to reach these noise analysis? And that's at the structural level. power analysis, does it actually consume a decent amount of power? Have you properly accounted for that? You know, design rule checking, did it meet all your design rules like we covered in section 1? ERC is error rule checking. That all ties into our different analysis. And parasitic extraction, have we designed it so that we remove parasitic delays? Let me bring this back for you. And so you start all the way up at your physical level, at your behavioral specification, and go down to your RTL specification, down to your structural, and then down to the physical level. So physical level, you were that CO2, that CO spotting. So what happens when you actually have improperly doped transistors, or you have atoms that aren't supposed to be in there that cause some sort of electron degradation, mobility degradation. How do you ensure that your transistors have been properly designed so that way your threshold voltage is proper? All of this stuff ties in there. So your physical specifications, let's say you're using a lot of pseudo NMOS because you want to try to reduce the size of the circuit. Then you worry about your timing analysis. Well, your timing is going to be a little slower. So you have to make sure that if it's communicating at this level with other circuits, it has to ensure that your control runs properly. If you run it too fast, you're not going to be able to get the switching to work down at this level, which means you're going to get unknown values, which means you're going to, at the RTL level, you're going to spit out incorrect values because you didn't meet your timing analysis. Does this make sense? All right. I want to go over a couple more things really quick here. How can you test chips? Well, you can actually put your test vectors on, write it in Verilog or VHDL, put it onto a board like you guys are doing in 386, bring your chip, hook up all the pins, and run it. So you know all of these. If you know, you can combine both of these topics into one thing. So hopefully you don't feel like 385 and 386 were complete wastes of time. No comment, please.
How often will I actually use MIPS then?
Depends on who you work for. Depends on who you work for. Yeah. I mean, if you work for an oil company, you're never going to use MIPS, really. But if you go and work for Intel or AMD, especially AMD, you would use MIPS a lot. You put ARM, they use a lot of ARM, but they do use a lot of MIPS. Intel, they have their own processors too. But MIPS is I've said this spiel before, but MIPS is a really good fundamental thing. Oh no, it's just look, example 6.2. I was debating whether or not to end, but because Thomas brought that up. So this is just a real quick thing. We'll end here, and I'll post the homework assignment. But consider testing the MIPS microprocessor. Those of you who had to do that last semester. Explain the difference between the test you would use for logical verification, silicon debug, and the test you would use for manufacturing. So I kind of have a little spiel here about logic verification should test that each operation can be performed, like I type, R type, J type, jumps, branch equivalent, make sure that so you have to test each element to make sure it's the timing that you need it. Logic verification will not necessarily prove that the instruction works for all possible addresses and data types. In contrast, manufacturing tests must prove that every gate operates correctly. So you're going to have different test vectors that will not only ensure that this logically works, but that you don't have stuck at faults. And then finally, when you're dealing with, you have to be stimulated to produce both a 0 and 1 to ensure the gate is not damaged. And then the manufacturing test may only be applied to the microprocessor prior to it being placed in the system. So we kind of gave an example. Therefore, clearly it is a challenge to devise a set of tests that are both complete enough. This is the end of the problem. But I just wanted to note, clearly it is a challenge to devise a set of tests that is both complete enough for customers to receive very few defective chips and short enough to keep the testing economical. And so next class, we are going to start discussing these certain algorithms that we're actually going to use, what happens when a chip fails, where can we find this, to give a preview. We're going to talk about stuck at faults. We're going to talk about observability and controllability. I'm going to close this up while I'm stopping.